Hello everyone and welcome to Geeks for Geeks. The problem which we are going to see today is to find the majority element. So in this problem you will be given an array A of size n and the majority element is basically an element that appears more than n by 2 times, and hence it is at most at most there will be only one such element. Okay, so we basically have to write a function which emits the majority element, and if there isn't a majority element, then it should basically print none. So let's understand it with an example. So in this array we have a total of 9 elements, and the output is 4 here. Why? Because 4 is appearing 5 out of 9 times. So 1, 2, 3, 4 and 5. So 4 is appearing 5 times out of total 9 elements. So that is why 4 is a majority element here. Now let's look at the another example. So in this example we have a total of 8 elements, but 3 is appearing 2 times, 4 is appearing 4 times, and 2 is appearing 2 times again. So none of the element is appearing more than n by 2 times. So that is why we have the output as none. Okay, so let's look at the method one. So this is the basic method. So it has the solution that you run two loops and keep a track of maximum count of all the different elements. If the maximum count becomes greater than n by 2, then basically break from the loop and return the value having the maximum count. If the maximum count doesn't become more than n by 2, then majority element doesn't exist. So you basically print none in this case. So the time complexity will be order of n square and the auxiliary space will be order of 1. So the question is, can we have a better algorithm? Yes, we can. So in this we will be using a binary search tree. So in the binary search tree we will be using this type of a structure where we will have an element and we will have the count. So this will be the value of the node and this will be the count of the node. So note that in binary search tree we do not have the duplicate values. So whenever we encounter duplicate value, we will be increasing the count value here. Let's see how it works. So we basically insert elements in the BST one by one, and if an element is already present, then we increment the count of the node. At any stage, if the count of the node becomes more than n by 2, then we basically return. This method will basically work best for the case where n by 2 plus 1 occurrence of the majority element is present in the starting of the array. So like in this type of an array, this is going to give the results very quickly. So the time complexity for this algorithm will be order of n square if we use a binary search tree. Whereas if we use a self-balancing binary search tree, then the time complexity will be reduced to order of n log n. In both of these, we'll be using an auxiliary space of order of n for the binary search tree. Okay, so can we do better? Yes, we can. This is actually significantly better. So let's see what Murray's voting algorithm does. So this will include basically two steps. The first step will be to get an element occurring the most number of times. By the end of this step of the algorithm, we will get we will get at least one element which is occurring the most number of times. Now, in the next step, we just have to check that if this number, which we got from the first step, is the majority element or not. So we basically get a candidate from this step, which candidate to be a majority element, and then we check if it's a majority element or not. So to find the candidate, the algorithm works in the time complexity of order of n, and it is called Murray's voting algorithm. So basic idea of the algorithm is that if we cancel out each occurrence of an element E with all the other elements that are different from E, then E will exist till end if it is a majority element. So this is the algorithm, Murray's voting algorithm. So here we initialize the majority index by 0 and count by 1. Then we loop from I equal to 1 to the size minus 1, and then we basically check if the element at majority index is same as the current element, then we increase the count. Otherwise, we decrease the count. That is the whole incrementing and decrementing thing which works here. Also, if at any point of the time the count becomes 0, then we again initialize the majority index to the current index, and we also reset the count value to 1. In the end, if in the end we will be actually left with a candidate for being the majority element. So this is whatever we discussed in the last slide is actually written here. So it loops through each element and maintains a count of a majority index. If the next element is the same, then increment the count. If the next element is not the same, then decrement the count. And if the count reaches 0 at any time, then change the max index to the current element and also set the count to 1. So the first phase of algorithm gives us the candidate element. In the second phase, we need to check if this candidate element is really a majority element or not. So second phase is also simple and can be easily done in order of n. We just need to check if the count of the candidate element is greater than n by 2. Okay, so let's understand the Murray's voting algorithm with an example. So suppose we are given this array. So for this element 2 here, we initialize the majority index as 0. So this majority index will be pointing to 2 here, and we initialize the count as 1. So now we are checking basically that if 2 is the candidate. So then we come here. Yes, this is the same element, same as element at majority index. So the count becomes 2. Now we come at 3. Well, this is different. So we decrease the count to 1. Now we come here again, 5 is also different than 2. So we decrease the count to 0. Now since count has become 0, so we'll change the candidate for majority element to 5. So this becomes our new candidate, and the majority index becomes 3, starting from the 0, 1, 2, 3. So the majority index becomes 3, and the count is also reset to 1. Now we will process 2 here. So this is different than 5. So they will decrease the count to 0. Since count has become 0, so we again change the majority element to 2. So this becomes the majority element, and the majority index becomes 4. Now we process this 2 here. This is the same as the majority element, candidate for the majority element. So the count becomes 2. Then we process 6 here. So this is different. So the count becomes 1. So in the end, we are left with the candidate for majority element, which is 2. Okay. So now we basically to check to print the majority element. What we do is we find a candidate for the majority. Then we'll actually check if that candidate is appearing more than n by 2 times. If yes, then we print the candidate. Otherwise, we print none. Okay, so let's look at the code. So this will be the driver function here. So we are given the array, we are inputting the size, and then we are basically calling the print majority. This is the print majority function. So in this print majority function, we get as an argument an array and its size. And we first of all find out a candidate by calling the function find candidate. And once we get that candidate, we basically check if it's a majority function. It's a majority element. So here we pass the array, the size of the array, and the candidate. If it is the majority element, we print that element. Otherwise, we print saying there is no majority element. Okay, so let's come here. So we first of all will see the find candidate function. So we initialize majority index with 0 and the count with 1. I is initialized as 1 here. Then we run a loop till the size of the array, basically size minus 1. Then we check if element at majority index is same as the current element. If yes, then we increment the count. Otherwise, we decrement the count. If at any point the count becomes 0, we initialize the majority index as the current element and the count as 1. After all this, we basically return the candidate, which is element at majority index. Once this is done, this will be passed to the candidate value here, and then we basically run a loop and check if it occurs more than n by 2 times. So we basically increase its count every time we encounter that element, and then we also check if the count has become greater than size by 2. Then we return 1, else we return 0. So the time complexity of this algorithm will be order of 1, and the auxiliary space that will be used will also be order of 1. Sorry, the time complexity will be order of n, and the auxiliary space used will be order of 1. So in total, we discussed 3 methods. So the first basic method has a time complexity of order of n square, which is not really that good. Then we discussed the method 2, where we were using binary search tree. So if we use a BFT, then we get a time complexity of order of n square. And if we use a balancing binary tree, then we get a time complexity of order of n log n. Now, this is also not that good. So if we use Moore's voting algorithm, which we discussed just now, then we get the job done in order of n time complexity, which is much better and the minimum possible time complexity. So that is all for this tutorial. You can visit this link to find all the material discussed in this tutorial and also run the code firsthand in the IDE present in the website itself. Thank you very much.